Okay, so let's look at states of matter. And I realize you've probably learned states of matter several times over your life, but that doesn't mean that you really know all the different parts. So if I ask you to visualize a solid, a liquid, or a gas, I think you can. But then if I ask a little bit more details about it, you may or may not be able to answer those questions. So the differences of solid liquids and gases is partly due to kinetic molecular theory. So kinetic molecular theory, or KMT, basically has to revolve around motion. So everything is in constant motion regardless of the state of matter. It's just whether or not we can tell. So what it does, it explains the forces between molecules, their energy, and the states of matter. There are three important assumptions. One is that the particles in a gas are considered to have insignificant volume. The motions of particles in a gas that happens to be rapid, constant, and random, and all collisions between particles in a gas are considered to be perfectly elastic. This means that when each collision, the kinetic energy is transferred without loss from one particle to another. So if this is molecule A, this is molecule B, what happens is they're going to come together, hit each other, and then they go their separate ways. It's a perfect bounce away. Okay, so this could be first step, they come together, hit each other, and then they separate in opposite directions. So that would be a perfectly elastic collision. The reality is, some of these assumptions aren't exactly valid depending on our temperature, our pressure, and the certain molecules that we have. Now, kinetic energy. What is kinetic energy? If you've taken physics, you'll be more familiar with this, but it is the energy of motion. So kinetic energy is equal to 1/2 times mass times velocity squared. But if you think about it, how would we do that in the chemistry world? If you have a bunch of gas molecules, how are we going to measure their mass? How are we going to measure the velocity of that oxygen in our air? So the reality is we're going to focus on temperature. So the higher the temperature, the faster the molecules move, the greater your kinetic energy. So what we could say is the kinetic energy of a gas is much higher than that of a solid. Now, a solid is moving. These are vibrating, really small vibrations. A liquid's a little more vibrations. And again, we just can't tell with our eyes. So there are different properties of gases. Gases expand to fill the container and they're compressible. There's lots of space between gas molecules. Airbags are actually made up of compressed gases that absorb pressure when they are impacted. Molecules will move in a straight line, however they travel in random paths. So what you can see here is there's a lot of space between those gas molecules. So when the piston goes down, it allows for the compression. And here it's just showing the random paths of those gases going beep, bum, bum, bum. Okay, nice straight lines, but totally random. We cannot control where those gases go. Kinetic energy is greater than the attractive force, allowing for increased movement. That's a property of gas. We can measure gas pressures in atmospheres, kilopascals, torrs, or millimeters of mercury. Okay, we can use a manometer or a barometer to do that. I would make sure you know these pressure units. So if I ask you to convert atmospheres to torrs, you can do that by using our dimensional analysis. Okay, so if you have trouble with unit conversions, please let me know. So I'd put that on a help sheet or write it somewhere that you can easily access because it is likely that you're going to have to convert your pressure units. This video is hyperlinked. It shows you how a barometer works. This is kind of a rudimentary one where you have a bunch of mercury at the bottom. The atmospheric pressure pushes down, allowing for the mercury to flow up. And you can see that the millimeters of mercury is actually a measurement of how high it goes up that tube. Torr is named after a guy, Torricelli. Kilopascal is named after Pascal. So factors that can have an effect on gas pressure. When we can increase our amount of gas, we can increase our number of molecules, and we can decrease our volume. And so I gave you a picture to kind of see those differences, like low pressure versus high pressure. And the minute you have higher pressure, you're going to have more collisions between your different molecules. Now with liquids, molecules will flow and stay together in the bottom of a container. Okay, so they'll also take the shape of a container. They are a little more random in movement than solids, but not as much as a gas. They do have definite volume and can take the shape of a container. I do want you to have the proper definition of a boiling point. The boiling point is the temperature at which the vapor pressure of the liquid just equals that external pressure. Okay, so vapor pressure is really the pressure right above. And so when that equals our pressure in the atmosphere or external that's in the room, that's when you get boiling. Usually we think of the bubbles in a liquid. So liquids at boiling point, the vapor pressure here, if we define it, is a measure of the force or pressure exerted by a gas above a liquid within a container. I'm not going to get into much detail of that this year. That's something I chose that isn't as important as some of the other things right now. An increase in temperature will increase your vapor pressure. Boiling point is pressure dependent. So the normal boiling point, this is at normal conditions, is measured at a pressure of 101.3 kPa. And so water's normal boiling point is 100 degrees C. What you'll find though, here in Colorado, we live at a very different pressure. Because we're at high altitude, you'll find that our boiling point is actually less than 100 degrees C. And because it's less than 100 degrees C, we find that it takes us much longer to cook things. Okay, so it's not as high, so we have to cook things longer. So here is showing at 760 millimeters of mercury. And here we could look at how different it is at Mount Everest with its atmospheric pressure at 250 millimeters of mercury. So theoretically, things would boil at a much lower temperature on Mount Everest, but it would take forever to cook something. Then you can see we're probably over here, right, in terms of altitude. Now, solids, molecules are held together by attraction forces due to their opposite charges. Ionic bonds are typical in our solids. Molecules will appear to vibrate about fixed points, and they have both definite shape and volume. So molecules are arranged in a fixed structure. Now, this picture and these things were like the back of the periodic table that I described first semester. It's the same idea. So I thought it would be useful to show you some different examples of some different compounds. So let's look at NaCl. So if we think back to Unit 1, I want you to think about which one, is it the green or the white that would be sodium, and which one would be chlorine. Okay, you can see they make a nice little lattice structure here. So if you realize chlorine is the green one and the white one is sodium, you are correct. Chlorine has gained an electron, making it negative, and an anion, which is larger. Sodium would have lost an electron, making it smaller. So I just wanted to remind you a little bit of first semester. Now there's something kind of fun. They're called allotropes. An allotrope is a solid that is able to have two different crystalline structures. Carbon is a really famous one for that. And so I'll talk about that in a moment. Sulfur also is well known, phosphorus, oxygen, and tin. So these are carbon's allotropes. And what you'll find is carbon has many different forms. It could be a diamond, it could be coal, it could be graphite. So diamonds have a structure kind of like this. There's lots and lots of covalent bonds, so it's super, super strong and used for like cutting tools. This second one here is graphite. And if you think about a pencil, it'll come off in sheaths. So this middle part here is strong, but not in between those. So this is like the pencil lead that you would see on your paper. This one here is called a buckyball or Buckminster fullerene. So each of these corners is a carbon. So there's a whole lot of carbons there. This is amorphous carbon. It's just a pile of carbon. It's kind of random. This thing here is a carbon nanotube. So you might have heard about nanotechnology. This has some really cool implications for the medical field. Now, non-crystalline solids are known as amorphous. Okay, so they will lack internal structure. Here's quartz or sand, which is silicon dioxide. And then here is our amorphous glass. And you can see how it has some defined, but not all. So I want you to start looking at things that are made of glass. And you can tell something if it's hand blown because you can see the shape isn't perfect usually. It's kind of a finicky substance, and it's kind of fun to really watch something like glass blowing So if you haven't checked it out, check it out. There's actually a Netflix show called Blown Away or something like that, and it shows glass flowing. It's pretty interesting. It's something I used to do actually. Now, a phase diagram will give us the conditions of temperature and pressure at which a substance exists at a solid, liquid, and gas. And a lot of this is vocab, and most of it I'm assuming you know. I bet you've heard of a freezing point or a melting point, vaporization and condensation. And notice I'm putting things as opposites. Sublimation is like dry ice. It goes directly from a solid to a gas. And if we go the opposite direction, that's deposition. There's also a point called a triple point, which is where the substance exists in all three states at the same time. So it's a solid, a liquid, and a gas. You have to have the exact temperature and pressure to do that, but it's pretty cool to do that. The critical point is a point at which a phase boundary no longer exists. This often happens with supercritical fluids. Okay, so it's like a blurry zone of the two phases. So this is a typical phase diagram. They all look a little bit different depending on the substance. You'll notice here is my freezing point and my boiling point. They are at the same pressure, so they are at 1 atmosphere. Okay, so you'll notice the green region is solid, yellow is liquid, and blue is vapor or a gas. You'll notice the triple point is right here, and that's where water would be a solid, liquid, and a gas all at the same time. Up here, this is our critical point where it's going to blur between a liquid and a gas region. Now we could draw arrows going from a solid to a liquid. That would be melting. And if we go this way, the opposite way would be freezing. We could go solid to a gas for sublimation, or the other way for deposition. So we could label this whole thing a little bit more. What I do expect you to do is if I give you something like 2 atmospheres and 75 degrees C and ask what phase it's in, you can go, oh, it's probably around here. You'd realize it's a liquid. And then if I say if we're at 2 atmospheres and 75 degrees C, and let's say it gets heated to, let's say 300 degrees C, you realize we've now gone from a liquid to a gas and that it has been vaporized. So hopefully you can understand how to read a phase diagram, and they all are going to have slightly different forms, but they usually will all kind of fit that format. So I put the practice problems on the formative this time, and there might be some stuff on CK12 as well. Here are some different phase or videos about the different phases in different ways, and then the gases activity we did in class.